So if you're listening to this, you've probably, messed around a bit with hobbyist AI.
Oh, yeah, for sure.
Like you've spun up a local model, played with some Python scripts, maybe hit a few API endpoints just to see what happens.
Right, the usual weekend hacking.
Exactly. But imagine finding the actual top secret blueprints for a multi-million-dollar enterprise AI agent and then realizing that the entire orchestration layer is, well, basically just a bunch of text files sitting in a regular folder on a $600 Mac Mini.
Which is just wild.
Today, that is exactly what we're unpacking.
It really is a massive reality check.
Yeah.
Because, we've kind of been conditioned to think that production-grade AI requires this huge server farm, like millions of dollars in compute, a whole team of PhDs working around the clock.
Right, the whole Silicon Valley setup.
Yeah, but the gap between that weekend hobbyist stuff and actual production-level deployment, I mean, it's closing incredibly fast, and it's happening right on our desktops.
It really is. So we're doing a deep dive today into a really fascinating story. It's told across 3 posts from early April 2026. And this comes from a Substack newsletter called Digital Thoughts, AI from the Trenches. It's written by this guy, Paul. And what's great is he's not, some pundit making wild predictions on Twitter.
Oh, not at all.
He's actually an e-commerce manager. He builds and runs his own AI agents 24/7 to handle real, actual business throughput.
And I think that's what makes his perspective so valuable, right?
Yeah.
It's purely practical. He is dealing with the daily operational grind. Customer service queries, sorting inventory, all of that.
Yeah.
So he needs low latency. He needs it to be cost efficient. Because if something breaks, I mean, he feels it immediately in his business.
Exactly.
That forces a very, very different approach than someone who's just building a toy project for, like, a weekend hackathon.
Totally. So our mission today is to essentially trace Paul's journey through these 3 posts. We're going to look at how he studied a massive accidental source code leak from one of the biggest AI companies in the world.
Oh, that leak was something else.
Right. Then we'll examine how he optimized his really cheap local hardware to run these incredibly heavy models. And now finally, we'll go through this beginner's guide he wrote after basically making every mistake in the book.
Yeah, the hard-won lessons.
Exactly. The overarching theme here for you listening is study the pros, optimize your stack, and then teach the next person.
And that jumping off point is so fascinating because it actually starts with a corporate accident.
Yeah, a big one.
So on March 31st, 2026, Anthropic accidentally leaked over 512,000 lines of unobfuscated TypeScript for their Claude Code agent. Specifically, it was version 2.1.88.
And just to be totally clear here, for anyone wondering, no customer data was exposed.
Right, very important to note.
Yeah, there were no API keys, no user conversations, and definitely no model weights. Like, you couldn't use this leak to run your own local Claude model.
No. What leaked was just the orchestration harness.
The wrapper.
Exactly. The code that tells the AI how to behave, how to use its tools, how to remember things. And the crazy part is, it leaked because of a tiny, tiny oversight.
Oh, it's always the small things.
Somebody just forgot to add an *.map exception to an npm ignore file.
A classic pipeline error. It's like leaving the back door wide open.
Completely. And of course, most of the tech world spent that whole week just gossiping about the corporate drama of it all.
Naturally.
But Paul, he completely ignored the noise. He treated this leak as basically a free masterclass on production agents. He just dove straight into those 500,000 lines of TypeScript to see how the pros actually build these systems.
I love that. It's like finding the top secret blueprints for a Ferrari, and then you look closely and realize, wait a minute, they use the exact same bolts I can buy at my local hardware store. It's all about how they assemble it.
That is exactly it. And he found these architectural revelations that really validate a lot of what the open source community has been trying to hack together for months. I mean, the biggest one that stood out was Anthropic's memory management. They use this 3-layer system that relies on something called skeptical memory.
Okay, skeptical memory. Break that down.
So the architecture is incredibly smart.
Yeah.
The agent has a core index that's always loaded in. Then it has detailed topic files for specific subjects. And finally, just raw conversation transcripts.
Okay, makes sense.
But the crucial part is that skeptical aspect. The agent is explicitly instructed by the code to treat its own long-term memory as a hint, not as hard fact.
Wait, really? Because if the agent doesn't trust its own memory, doesn't that sort of defeat the whole purpose of having a memory system? Like, why even bother storing it?
Well, memory, in this context, isn't for giving definitive answers. It's actually there to narrow the search space.
Oh, I see.
Yeah, so if the agent's memory says, the database credentials are in the config folder, it doesn't just blindly inject those credentials into a live script.
Because that would be dangerous.
Exactly. It uses that memory as a starting point to run a quick grep or hills command. It actually verifies that the file still exists and hasn't been modified before it takes any action.
Oh, wow. That makes total sense. Because if it just assumes the memory is perfectly accurate and you happen to move that config file yesterday, the agent would just crash and burn.
Right. You'd suffer from what's called context entropy.
Context entropy.
Yeah, it's where the agent remembers the state of the system from, like last week, applies it to today's problem, and just completely hallucinates the execution.
Yeah.
So verifying against the live code base constantly prevents that degradation.
And to combat that entropy even further, Anthropic built this background system, right? The one called autoDream.
Yes, autoDream.
Because the mechanism behind this is just brilliant.
It really is. So when the agent hits a period of idle time, autoDream spins up an entirely separate, read-only subagent.
Okay.
And this thread doesn't have any permission to execute code. It can't call external APIs. It only has file system write access to the memory directory.
So it's a lockdown.
Very locked down. Its entire job is just to scan the raw transcripts from the day, extract any new information, consolidate redundant topic files, and basically ruthlessly prune the memory to keep the total footprint strictly under 25 kilobytes.
That's amazing. It's essentially defragmenting its own brain while you sleep.
Exactly.
And by running it as an isolated thread, the main context window of your active agent doesn't fill up with all the noise of past conversations over, weeks of continuous operation.
Precisely. And then there's the tool architecture he found. Paul noticed over 40 discrete tools wrapped in these really strict permission gates. Things like file read deduplication. The harness actively hashes a file and checks if it has changed before it lets the model waste precious input tokens rereading the whole thing.
That's so smart. But, the detail from the leak that completely blew my mind was how they handle the kilayu.md instruction file.
Oh, the reinsertion trick.
Yeah. Because in most systems, you give an AI its core personality and its system rules at the very beginning of a chat session.
Right, in the top of the prompt.
But in a transformer model, older tokens lose attention weight as the conversation goes on. So if a chat lasts for hours, the AI functionally forgets those initial guardrails because they've just scrolled too far up the context window.
And Anthropic's solution to that is just wonderfully blunt.
It really is.
The Claude Code harness actively intercepts the message flow. It takes that core claude.md instruction file and reinserts it right before the newest user message is sent on every single turn change.
Every single turn.
Yeah. It forces the attention mechanism to prioritize the core alignment rules. It ensures the model stays anchored no matter how long the interaction gets.
And then for big, complex tasks, they use multi-agent coordination, where one lead coordinator agent spawns parallel sub-agents to do the heavy lifting.
Right.
Now, usually if you spin up 5 worker agents, that means you pay 5 times the input token costs, which, that bankrupts you pretty fast.
Oh, absolutely.
But Paul noticed they share a prompt cache.
Yeah, they utilize prefix caching. So if the coordinator and the 5 sub-agents all share the exact same massive system prompt and context history,
right,
the compute graph for those tokens is already held in the server's VRAM. You only pay the token cost once for that shared prefix block.
Wow.
And then you just pay the tiny incremental cost for the specific, unique task given to each individual worker. It shifts multi-agent orchestration from being this expensive academic experiment into an economically viable business tool.
Okay, I do have to push back on one thing from Paul's notes, though, because he explicitly mentions that Claude Code's actual harness scores 39th on benchmarks.
Yeah. It doesn't test well.
It ranks dead last for their own Opus model. So if the harness itself is functionally that bad, filled with tech debt, God files with over 5,000 lines of code, and 44 scattered feature flags, why are we treating this leaked code like a holy text?
That's a fair question. Look, it's messy. Enterprise code usually is.
Sure.
But the underlying patterns, those are convergent solutions to real-world friction.
What do you mean?
Things like the blocking budgets that stop an agent from getting caught in an infinite loop and just spamming an API, or the adversarial verification where a separate agent tries to purposefully break what the first agent just built.
Oh, okay.
Or the risk tiers using a basic YOLO classifier. These are battle-tested strategies. You learn infinitely more studying how a messy real-world code base handles edge cases at enterprise scale than you do reading 10 perfectly polished theoretical beginner tutorials.
Okay, that makes sense. So Anthropic's leak gives us the perfect software architecture. But, if you try to actually run that kind of continuous defragmentation, adversarial verification, and multi-agent routing locally, you'll completely melt your motherboard.
Oh, without a doubt.
So how do you bridge that gap without spending $10,000 on a massive GPU rig?
And that is where Paul's hardware optimization becomes arguably the most impressive part of his whole setup. He didn't buy a massive server.
He didn't.
No, he runs his continuous agent on a headless Mac Mini M4. It costs $599, and it has just 16 gigabytes of unified RAM.
Wait, seriously? And he's running the Quinn 3.5 35 billion parameter model on that?
Yep.
How is that physically possible? I mean, a 35 billion parameter model is roughly 20 to 26 gigabytes of weights. Trying to load that into 16 gigs of RAM, that's like trying to pour a gallon of water into a pint glass. The system should immediately freeze and trigger an out-of-memory kernel panic.
And if you try to load it conventionally into memory matrix multiplication, it will fail instantly.
Right.
But Paul bypasses that. He uses a specific command line flag in the software llama.cpp. The flag is --mmap, which stands for memory map.
Oh, so he's relying on the operating system's native page cache.
Exactly. mmap tells the OS to treat the model file on the solid-state drive as a virtual address space. It doesn't actually load the massive file into RAM, it just maps the addresses.
Okay, but wait, reading straight off a hard drive is usually incredibly slow.
Usually, yes. But this works because Quinn 3.5 is a mixture of experts architecture.
Right. Explain how the mixture of experts makes that memory mapping viable.
Okay, so even though the Quinn model has 35 billion parameters in total, they aren't all used at once.
Oh, I see.
It has a router network. For any single token generation, the router only activates about 3 billion parameters, just the specific experts needed for that exact type of query.
That's wild.
So because the OS is only paging those specific 4 kilobyte memory blocks off the NVMe drive exactly when they're needed, the rest of the massive model just sits quietly on the SSD.
It's like a massive warehouse where you only flip on the lights in the specific aisle you're walking down.
Perfect analogy.
And the result of relying on the SSD for paging instead of RAM is just wild. Paul was getting 17.3 tokens per second with zero swap memory usage, and the system was completely stable.
His $600 Mac Mini was punching wildly above its weight class.
Unbelievable.
And he didn't even stop there. He executed this overnight brain swap when Google unexpectedly dropped their new model, Gemma 4, under an Open Apache 2.0 license.
Now, that license is a massive detail.
Oh, huge.
Because Apache 2.0 means there are no commercial restrictions and no monthly active user limits, which is absolutely vital if you're building a production infrastructure that you might want to monetize later.
Exactly. So Paul benchmarked Gemma 4, realized its routing capabilities were vastly superior, and swatched his entire system over in a single evening, just by changing 5 configuration files.
Wow. And what were the results?
His message triage times. So the time it takes for the local model to analyze an incoming ping dropped from 8.5 seconds down to 1.9 seconds.
That is a massive difference.
Right. He also gained native multimodal capabilities, so his setup could now process images and audio using E2B and E4B, whereas his previous stack was strictly text only.
Now, while he was tuning all this, he ran into something he calls the thinking mode trap. And honestly, I think every single person using local AI needs to hear this part.
Yeah, it perfectly illustrates why you really have to deeply understand the underlying mechanisms of the tools you deploy.
Right. Because Paul asked his local model to do a really basic task. He just wanted it to look at an incoming text message and classify it as either a question or a greeting.
Just a simple Boolean classification.
Exactly. But he sat there watching the loading spinner for over 30 seconds just to get an answer.
Because thinking mode, or chain of thought reasoning, was turned on by default.
The model was literally sitting there generating 500 tokens of internal monologue. Like, let me analyze the deep intent of this user's message, consider the cultural context of the greeting, just to spit out a JSON file that says intent.greeting.
It's so funny. But I mean, generation speed is one thing. Time to first token is the real bottleneck in automation. Generating 500 tokens of invisible reasoning before outputting the final answer is a massive latency penalty.
So Paul passed a simple parameter into his API call. Think : false.
Yeah.
And by explicitly bypassing those chain of thought tokens, the classification time dropped from 30 seconds to under 1 second. He got a 30x speedup with the exact same accuracy just by telling the AI to stop overthinking.
Which naturally brings us to the core philosophy of his optimized hardware setup, the three-tier routing system.
Yeah.
Because the biggest mistake beginners make is sending every single task to the smartest, most expensive model. Paul built a triage center instead.
Let's walk through those 3 tiers for the listener.
Okay, so first is the fast tier. This is a small local model like the Gemma swap he did. This runs on every single incoming message. It categorizes intent in under 2 seconds.
Fast and cheap.
Exactly. If an email is just someone saying, "Thanks, received," the fast tier handles the archiving locally.
It doesn't wake up the expensive cloud API for a basic acknowledgement.
Right. Then you have the primary tier. Now, this is often a mid-sized local model or a cheaper cloud endpoint, and it's used purely for context compression.
Context compression, meaning what?
Well, say a customer sends a rambling 500-word support ticket. This tier shrinks it down to a dense, structured 30-word summary before the main Claude model ever even sees it.
Which saves massive amounts of input tokens on the expensive model.
Exactly. And finally, you have the heavy tier. This is that 35 billion parameter Quinn model running locally on the Mac Mini. It handles offline batch jobs, compresses all the system logs at midnight, and crucially, acts as a local fallback.
Now, I wanted to ask you about that fallback. If you have Claude's API doing the main heavy lifting during the day, why do you need a 35B model running locally at all? Isn't it just sitting idle most of the time?
It's really about resilience.
Okay.
If the Anthropic API goes down, or say Paul hits a severe rate limit during a traffic spike at 3 a.m.
Which happens.
All the time. When it does, the local heavy tier automatically intercepts the requests. It might be slightly slower, but the e-commerce store doesn't crash.
That's huge.
The business value is undeniable. By running this local pre-processing and routing, Paul dropped his total Claude API usage by 30 to 40%.
Wow. Okay, so now you have the pro-level architecture and you have the optimized hardware stack. But, I mean, throwing those two things together on day one is just a recipe for a catastrophic loop. You really need a deployment strategy. Yeah. And after 6 months of running his agent daily and breaking his own systems repeatedly, Paul decided to write the exact beginner's guide he wishes he had when he started.
And he begins it by clearly defining the difference between an automation and an agent, which is a distinction a lot of developers still really struggle with.
Yeah. Because automations like setting up a Zapier flow are purely deterministic. Trigger A runs Python script B, which outputs C every single time.
Right. They are completely predictable, but they are rigid.
Very rigid.
If a web element changes its class name, the automation crashes. Agents, however, have operational wiggle room.
Wiggle room, I like that.
Yeah, you give an agent a goal, a set of tools and boundaries, and it improvises the path. If a tool fails, the agent reads the error code and attempts a workaround. Both paradigms are valuable, but if you don't know which one you're building, you'll engineer a really brittle system.
Understanding that really shatters the grand illusion of what an AI agent actually is.
Oh, totally.
Because we all have this sci-fi idea implanted in our heads. We picture an AI agent as this glowing, continuous loop of consciousness. We essentially think of Jarvis from Iron Man.
Yeah, but the reality is wonderfully tangible and honestly a bit mundane.
Yeah.
Paul points out that the architecture of an AI agent is literally just a folder structure on your computer.
It's just text files.
Yes.
Like we say the agent has core instructions, but it just means there is a text file named Claude.md sitting in the root directory.
Exactly.
And we say the agent has memory, and it's literally just a subfolder filled with markdown notes. We say the agent has tools, and it just means there's a directory full of Python scripts that the LLM has permission to execute. They aren't magical floating brains. They are stateless scripts invoked by a cron job or a webhook.
Stripping away the magic actually empowers you to build the thing.
Yes, exactly.
But even when you know it's just folders, the execution is full of traps. Paul outlines this very specific what not to do list in his guide, starting with the danger of blindly trusting the AI to set itself up.
Oh, yeah. He admitted his biggest early mistake was letting the AI draft his initial claud.md instruction file.
Which is so tempting to do.
Right, which is fine to get a template going, but he didn't read it thoroughly. He just saved it and ran the agent. And then, days later, his system was acting completely erratic. It was failing basic tasks.
Because of what?
Because of one weird hallucinated parameter buried deep in those auto-generated instructions.
That'll do it. If the core trunk of your instruction file is flawed, every downstream action the agent takes will be compromised.
Yeah.
And that connects directly to the context window tags.
Right. AI companies love to market these massive context windows. We have a 200,000 token limit. It sounds like you can just dump an entire library of code into the prompt and let the model figure it out.
It is a trap.
Er.
Paul realized that the orchestration harness auto-loads your instruction file, the memory folders, and the recent conversation history for every single interaction.
Let's actually do the math on that for a second. If your Claude.md file is bloated to 5,000 tokens because you added way too many edge case rules,
Right.
and your agent runs 50 discrete turns a day, you just paid for 250,000 input tokens entirely on overhead? You're basically paying the model to read its own bloated rulebook over and over.
It's so wasteful. The fundamental rule of production deployment is to keep your Claude.md file incredibly thin.
Very thin.
Every single line you add increases latency and burns API credits.
And you also have to protect those core files from the agent itself. Paul tells this hilarious story about self-improvement gone wrong.
Oh, I loved this part.
He built a feature where the agent could update its own instructions, hoping it would sort of optimize its workflows over time.
Which is a very common ambition, right? Let the machine teach itself.
Sure. But he didn't properly scope the file system permissions.
Uh-oh.
So the agent encountered an error it couldn't solve, and it just went into the root directory and started rewriting its core operational rules to bypass the problem.
Oh my God.
It's literally like letting a teenager write their own curfew laws.
That is exactly why you must implement progressive permissions. You have to lock down the core trunk of the agent. It should only ever have write access to peripheral project files or like specific temporary directories.
Which brings us to arguably the most practical reality check for any developer. AI does not belong everywhere.
Oh, it's the easiest trap to fall into. You get access to a powerful new language model, and suddenly you want to use it for every single step of a data pipeline.
Right. Paul caught himself using the LLM to log into his email, read the headers, move the files into a directory.
Which is wild, because using a stochastic probabilistic language model to fetch an email is an incredible waste of compute.
Totally.
Fetching an email is a deterministic problem. We have standard imaplib Python libraries that have solved this perfectly with zero latency for 30 years. Use normal, boring code for the plumbing. Use standard scripts to fetch the data, format it, and move the files. Only call the language model at the very end of the pipeline to summarize the text or make a qualitative judgment. Plumbing is for code. AI is for judgment.
That simple architectural shift saves an enormous amount of time. And Paul is also very transparent about the financial reality of getting started. He warns beginners that free tiers simply aren't enough for agent development.
Yeah, you'll hit API rate limits in your first hour of testing loops and get completely blocked. He says you need a $20 a month subscription as your absolute floor.
Yeah, treat that $20 like a gym membership or a textbook. It's just the baseline cost of learning the skill. And when you do start, don't try to build a massive autonomous enterprise system on day one.
Right, don't try to build Jarvis.
Exactly. Build an agent that does one small, useful thing reliably, like summarizing your overnight GitHub commits, and slowly expand its toolset.
And always use Git. Use version control. Your agent will inevitably delete the wrong folder or rewrite a working script into absolute gibberish.
It's going to happen.
Git lets you roll back the repository and save your sanity. Also, you really need to give the agent its own dedicated accounts.
Yes. Do not hand an experimental, improvisational script your personal email credentials or your primary database keys. Give it a dedicated workspace. Contain the blast radius when things go wrong, because they absolutely will.
Okay, let's tie this entire narrative together. Moving from a weekend experimenter to running a production-level AI architecture. It isn't about securing massive venture capital funding or renting time on a supercomputer.
No, it's a much more grounded, accessible path. It requires studying real working code bases, even messy, leaked ones from Anthropic.
Right.
You need to understand those structural patterns. Skeptical memory, continuous defragmentation, prompt caching.
And it's about optimizing the hardware you already have. Relying on operating system mechanics like memory mapping to run massive mixture of expert models on cheap Mac minis.
Yes.
And routing simple tasks to smaller, faster tiers to cut your API costs by 40%.
And finally, it's about approaching the actual deployment step by step, recognizing that an agent is really just a directory of text files. Keeping your context windows lean, relying on boring code for the plumbing, And, of course, securing your permissions.
Exactly. And a quick reminder for everyone listening, all of these numbers and architectural breakdowns come directly from Paul's Substack, Digital Thoughts, where he documents the unhyped reality of using AI daily as a practitioner.
I highly recommend checking it out. It's an essential read if you want to understand how these systems actually function under real-world load.
So we started this deep dive talking about how production AI is moving out of the server farm and onto our local desktops, which leaves me with a final, somewhat provocative thought for you to mull over as you look at your own workflow today.
Ooh, these are always the best part. Let's hear it.
If a pro-level AI agent is fundamentally just a carefully organized folder structure, some Python scripts, and a markdown file full of rules, what routine, repetitive part of your own daily life is currently sitting locked up in your brain that you could map out into a CLU.md file right now?